Remember that the entropy for a process is going to be related to the heat transferred and the temperature at which that heat is transferred. So that's going to be heat transferred into or out of a system. And for an isothermal process, one that's happening at constant temperature, we can write the following. And we can adjust this if we're assuming something is happening at constant pressure. So we have to remember that at constant pressure, Q is equal to delta H, so we can rewrite our entropy expression. If we want to talk about something a bit more broad than system and surroundings, we can talk about the universe as a whole, which is composed of both the system and the surroundings. And remember, for a spontaneous process, the universe's entropy increases. And we can combine these different expressions from this slide and the previous one to give us an expression for delta S universe that includes delta H. And if we multiply both sides of this expression with a negative t, we'll end up with the following. And in and of itself, this equation is not particularly useful, but we can convert it into something that is considerably more useful. That negative t delta S universe term that we just saw is related to the spontaneity of the process being examined. And that term is actually given a specific name. It's called the Gibbs free energy. And because it's related to spontaneity, when the entropy of the entire universe increases, that's spontaneous, and that gives you a sign of delta S universe that's positive, right? Positive related to an increase. So negative t times a positive value gives you a negative number. So when delta G is negative, you have a spontaneous process. So we have a couple of different situations here. We can have three values of delta G. We can have a negative value, we can have 0, and we can have a positive value. And we saw earlier that a negative delta G, a delta G less than 0, means you have a spontaneous process. If you look at that in terms of an equilibrium reaction, it means you have spontaneous movement in one of the directions of that equilibrium. So in the example on the screen, you have N2 and H2 converting into ammonia, and a negative delta G implies a spontaneous forward reaction. And that means you're going to be making products faster than you're making reactants. So you can also relate delta G to a Q value, which means you can also relate it to a K value. So a negative delta G implies that for an equilibrium reaction, Q is less than K. And in the other delta G regimes, you have different situations. So a delta G that's positive implies non-spontaneous. So this is a bit odd. If your delta G is positive, what it implies is for the reaction that's written, in this case N2 plus 3H2 going to 2 NH3s, if your delta G is positive, the reaction is non-spontaneous in the forward direction. So if delta G is positive, it means that you are not making NH3 faster than you're making the reactants. A delta G that's positive is non-spontaneous in the forward direction, but it is spontaneous in the reverse direction. And our third possibility is that delta G is equal to 0. A delta G that's equal to 0 implies that the system is at equilibrium. You're making products and reactants at equal rates. So earlier we learned an expression for delta G, the free energy. We saw that delta G was equal to a change in enthalpy minus temperature times a change in entropy term. And we can look at how this expression is related to the temperature term. So there are two general components to the Gibbs free energy. We have an enthalpy term and we have an entropy term. And if we change the temperature, we're really changing the magnitude of that entropy term. So let's consider an example. So if you look at the dissolution process for ammonium nitrate, it splits up into ammonium ions and nitrate ions, and this reaction is endothermic. So if you dissolve a bunch of ammonium nitrate in water, the ammonium nitrate splitting up into its ions is going to absorb heat from the water, and the water will actually cool down. So this process is endothermic. The splitting up is delta H is positive, and it's spontaneous. That happens automatically. You don't have to do anything. You just dump it in the water and it splits up. Another reaction is sodium chloride in water. This reaction is exothermic, and it's spontaneous as well. The sodium chloride dissolves, it splits up into its ions, and it releases a little bit of heat, and it actually warms up the water. Of these two reactions, both are spontaneous, and only one of them is actually going to increase entropy. Of these two reactions, you have an endothermic reaction, you have an exothermic reaction, you have two spontaneous reactions, and you have reactions where the stoichiometry is identical. So the only real difference here must come from the entropy term. So in order for a reaction to be spontaneous, delta G has to be negative. And that implies that the entropy for these two reactions, the entropy change for these two reactions has to be very different. And that's where the temperature dependence is going to come in. So this is a table showing all the different signs of delta H, delta S, and delta G that you can have in order to get spontaneous reactions or non-spontaneous reactions at different temperatures. But the most important thing here is that you don't need to memorize the table. You can work all of this out for yourself using the delta G expression. So in our previous example where we had ammonium nitrate, that was a spontaneous reaction. So we know that delta G is negative. That reaction was endothermic. It cooled the water down. So that means that delta H was positive for the process. And we don't really know anything about the entropy yet. We don't know the temperature at which it happened. But we do know that that T delta S term has to be a bigger value than the delta H term. Otherwise, the delta G could never be negative. Something else also gets revealed here. Because there's a negative sign in front of the T delta S term, we know that the sign of delta S must be positive if we're going to have a negative delta G. So we know that the entropy change for ammonium nitrate dissolving must be positive. There must be an increase in entropy. And if we have numerical values for delta G, delta H, delta S, we can work out a temperature at which spontaneity can happen, at which non-spontaneity can happen, and at which equilibrium can happen. Remember, at equilibrium, delta G is 0. So it's possible that we can set delta G equal to 0. We can use a delta H for a reaction and a delta S for that reaction, and we can work at the temperature at which the reaction reaches equilibrium. So we can do some simple calculations with this. If you want to calculate a delta G for a reaction for which delta H is 24.6 kilojoules, delta S is 132 joules per Kelvin, we know the temperature, we can calculate a delta G. An important thing to note here is that our units don't match. We have joules and kilojoules, so we have to get everything into the same units. And then we can calculate the value for delta G. If delta G is negative, the reaction is spontaneous. If it's positive, it's non-spontaneous. And if it's 0, the reaction's at equilibrium. A similar question is for the reaction of nitrogen plus hydrogen to give you ammonia. Assume that delta H and delta S remain constant, what happens to the delta G if the temperature increases? Well, all that can happen here is that the size of your T delta S term is going to increase. And since the size of your T delta S term is the only thing that's going to change if temperature changes, in order to determine the effect on delta G, you have to know the sign of delta S. Is an increasing temperature going to make that T delta S term bigger or smaller? And just from looking at the reaction, you can estimate the sign of delta S. Here everything is a gas, but you're going from 4 molecules of gas on the left-hand side of the reaction to 2 moles of gas on the right-hand side. So you're going from a more complex system to a less complex system, so you're losing entropy. So the sign of delta S here is negative. So if you increase the temperature, you're going to be increasing delta G. Because you're increasing the temperature that's multiplied by a negative value, and then you're subtracting that entire term, you have effectively a negative times a negative, which is a positive. So if you increase your delta T, you increase your delta G. Now, it's important to note that this is only true if your delta S is negative. If your delta S is positive, the opposite happens.